So we'll try and answer this question. And we use AC a lot during the theory of cardinals. I mean, the main point is that the AC is equivalent to the well-ordering principle. So that means that every set can be well-ordered. Well, it's equivalent. So given any set X, there's some relation on X cross X so that X with the less than relation is a well order. Now we use the fact that any well order is isomorphic to an ordinal. So I say that some f that goes from X with less than isomorphically, so a bijection which preserves the order to an ordinal, alpha, say, and less than coincides with epsilon on ordinals. So for cardinality concerns, we're not too bothered about this well ordering, but we're bothered that there is such an F. This allows us to say that F is bijective with an ordinal. Without AC or WP, we would not be able to say that there is such a bijection even between X and an ordinal. So without AC, we might not be able to say that there is a bijection between X and an ordinal. I mean, for special sets, yes, right? We could perhaps prove such, right? But in general, we may not have that there is such an F. Right? So to get a theory of cardinality off the ground, we use the well ordering principle. We assume basically sets can be bijected with ordinals. So to get cardinality theory going, we assume the well ordering principle. Now, you don't have to do this. I mean, some introductory texts will just not assume this, and they'll try and introduce cardinals without assuming sets are bijective with ordinals. But then it becomes difficult, because then you ask, well, what are cardinals? When you've got that sets are bijective with ordinals, we've got a ready and handy definition of what the cardinality of X is. It's the least alpha bijective with X. We use ordinals. I mean, some ordinals can play the role of cardinals. But if you don't have this bijection property, then you have to say what cardinals are. And they aren't all ordinals. They'd have to be something else. So the theory of cardinality goes very wonky if you don't have AC. If you try and develop it, then you find that cardinals are partially ordered rather than in a strict total order. So we don't bother with all of those refinements at the moment. We just assume AC and keep things simple. Okay, so we in fact use AC a lot, even to talk about cardinalities, to make much sense of cardinalities. But in that particular lemma, I mentioned AC because it played a kind of crucial role. So first thing to notice in the question here is, I said, if kappa is a regular cardinal, the union of less than kappa many sets, each of cardinality less than kappa, is of cardinality less than kappa. So note, kappa must be regular for the question to make sense. For example, so as a counterexample, if I take kappa to be singular, for example, aleph omega, so we can consider, here are the sequence of the aleph n's. What have I got? I've got an omega sequence, an aleph 0 sequence of sets, each of which are cardinality less than kappa. So less than kappa many sets, all of size less than kappa. But the union of the sets is aleph omega. So here would be aleph omega. Here's the ordinal line going up here, aleph 0. And here are the aleph n's. So these go up cofinally into aleph omega. And their union of these ordinals is this ordinal. So this will be a counterexample to the question when I've got a singular kappa. I can approach aleph omega using a small sequence, a short sequence of small sets. Now, but when kappa is regular, it's a different question. So let kappa be regular. In fact, it's easiest, or perhaps clearer, to start with kappa being a successor cardinal. So as kappa is lambda plus. So it's a successor cardinal rather than a regular limit cardinal, if such exist. So kappa is lambda plus with lambda a cardinal. Okay, so here's kappa, it's lambda plus, and here's lambda. Right, so lambda could be aleph n, and kappa could be aleph n plus 1. But in general. So now let x tor be tor less than lambda be a sequence of lambda many sets with each, and the cardinality of the x tors is less than or equal to lambda. Now you could say, well, what if, okay, beta is an ordinal that's less than kappa here. I'm going to give you a beta sequence of sets, but I can always rearrange those to form a lambda sequence because there's a bijection between beta and lambda. So this isn't really part of it. Any beta sequence, x prime tor, for some beta between lambda and lambda plus, can be arranged into a sequence like this. So I'm just talking around it. Because there is a bijection between lambda and beta. So I don't really need to bother with sequences which are longer than lambda. Right? I can always rearrange it we're only talking about size here. We're only talking about cardinalities, not about orderings. So I'll just reorder a beta sequence so that it looks like a lambda sequence. Okay, so this is the setup. I've got less than kappa many sets, each of cardinality less than kappa, which means less than or equal to lambda. Okay, is everybody happy with the setup? Okay. Now we use, from the third year set theory course, right, that there is pi, and it's a bijection between lambda cross lambda and lambda. Okay. So this came as a corollary to Hessenberg's theorem, or perhaps it was part of Hessenberg's theorem. If you want to look up those notes from that course, there we showed something like cardinal multiplication, lambda times lambda was lambda. That's what we're using here. So there's a bijection between this Cartesian product and lambda. And now if I've got this, it's kind of easy, right? I take the collection of x's, the x tors I've got, I take some function f here, right? I look at the union of the x tors, tor less than lambda, and I send this to lambda. And what do? I look at the least, I pick an element of this. The x tors may overlap. I haven't said they have to be disjoint. Right? So I pick an element in here, and I just look for the least tor such that it's in that x tor. So let's take some z here in this union. So let tor of z be the least tor such that z is in x tor. Yeah, it may be in many x tors, but there's a first one, right? And now each of the x tors has got size less than or equal to lambda. So I probably should have said this bit first, actually. So there's a bijection, or rather there's a map. Let's say G tor which takes x tor into lambda, right? 1 to 1. Because this has got size less than or equal to lambda. So now what I do is put these ideas together. I still haven't finished my definition of f yet. This bit here. I could have said this bit earlier on, much earlier on. I could have put it up here. So getting late on a Friday afternoon, I think. Yeah, I should have put this bit up here. So we want to define back to F. I pick an object in the domain of F, Z. I find the least Tor such that Z is in X Tor. Right. So I can apply G Tor to Z here, and this will give me something in lambda. So I let F of Z, I can just let that be the least pair Tor Z here, and then G Tor of Z. So I've got here something in this Cartesian product. Here. So I haven't quite got F here. Let's call that F0 of Z. And then finally, we'll let F of Z be, I'll apply pi to this pair. So that's in lambda. So pi is a bijection. Yeah, so this is one-to-one onto over here. So each pair goes to a unique ordinal less than lambda, and conversely, here. For any Z, there's a unique Tor Z that's associated with it. So I then look at the one-to-one map here, and G of Tor takes different things in X Tor to different ordinals. So in the end here, what I've got is that F is a one-to-one map into lambda. But that says the cardinality of this is less than the cardinality of that. Which is what we were trying to show. Perhaps I made slightly heavy weather of that. I mean, but anyway. So what we did there was we assumed that it was a regular successor cardinal. Right? To complete the story, I should argue, or you could ask me and say, well, what happens if it's regular and a limit cardinal? Right? What do we do now? Well, we just vary the story here. I thought of splitting it into two cases, although I could have just given this case, right? Because I thought it might be more understandable. So in general, kappa may not be a successor. So the argument is just a variant. So now I've got this set here for Tor less than some delta. And I know that delta is less than kappa. And for each Tor less than delta, there is G Tor that takes X Tor here, bijective with some cardinal. What shall I call it? Eta Tor here, and that's also less than kappa. So I'm resetting the problem up. I've got a less than kappa sequence of sets, and each of them is of size less than kappa. So I've got a bijection between the set and a cardinal less than kappa. So this double arrow thing means it's 1-to-1 on 2. So it's the same setup without pretending that kappa is lambda plus. Okay. So there was one crucial point where we use the regularity of kappa. So I'll say let eta be the supremum of the eta tors. All right, so the delta many of these. Here's kappa. Here's a typical eta tor down here. But there's not many of them. There's less than kappa of them. So even if these were an increasing sequence of these eta tors, kappa's got cofinality kappa, not delta. So the supremum of these is less than kappa. So eta is here. Since kappa is the cofinality of kappa, okay, which is bigger than delta, eta is less than kappa. So altogether, all of my data is bounded by this eta. Right? There's only delta many things. They've all got, well, I suppose it's conceivable that delta is up here. But in any case, delta, the maximum of delta and eta is less than kappa. So let eta tilde be the maximum of delta and eta. Perhaps delta's up here, in which case delta would be this eta tilde. Or maybe delta's down here, in which case eta is eta tilde. Anyway, the larger of the two. And now we kind of do the moves that we just had in the first part. Suppose let pi is a map from delta cross delta to delta. Right here, I could say let for z in the big union, tor less than delta here, I'll let tor of z equal the, now I'm just repeating myself, the least tor such that z is in x tor. Okay. We first defined f0 of z as an ordered pair, tor of z, and then where g tor took z. Like this here. And now where I've got something that is in eta tilde cross eta tilde. So I'm just allowing myself a little bit of room there, right? And right, so what I want is pi to be from eta tilde here to eta tilde. Sorry, not delta. And then I can let f of z be pi of f0 of z here. And so then this is in eta tilde. Right? And well, I should have made the obvious remark that kappa is bigger than eta tilde. So f takes the big union here, 1-to-1, into eta tilde. And so its cardinality is less than kappa. It's less than or equal to eta tilde. So we're done there as well. Okay, so perhaps slightly easier to think about when kappa is lambda plus, but it's essentially the same argument. Okay, so hope there any questions about that? No? Or is that all right? So send through if you want me to do anything particular. I could go over the last homeworks that were not the ones that were set. But things related. I'm just seeing if there are any more questions. So there's another question about the exercise 215. Here. Okay. So this was about cofinality. So find Sn contained in aleph omega plus 1, which is stationary, and the sets are decreasing like this, and their intersection is empty. So this is to contrast with the case of closed unbounded sets. This is a regular cardinal. It's a successor. It's aleph omega plus. It's a regular cardinal. If these were all CUB sets, the intersection of less than this many CUB sets will be CUB, but in fact, it's designed to be empty. So the intersection of stationary sets, of course, even if they're descending like this, could be empty. So the idea is to just generalize the idea about cofinality. We saw if we looked at, so I looked at this here, collection of ordinals less than omega 2 who've got cofinality omega. And I could do it again for omega 1, yeah, which have got cofinality omega 1. Now, here at omega 2, here's omega 1, and here's omega 0. So below omega 2, there are two regular cardinals. Cofinality is always regular cardinals. So below omega 2, I've got two possibilities. If you give me a limit ordinal alpha, maybe it's got this cofinality, maybe it's got this. So for the limit cardinals, these below omega 2, they're partitioned into two kinds, things in this set or things in this set. And of course, they're disjoint. You can't have cofinality. You can't approach an ordinal through an omega sequence and an omega 1 sequence. So both T omega and T omega 1 are stationary. Right. But here they've got empty intersection. Okay, if I replaced omega 2 by omega 3 here, I could now define 3 sets, right? Below omega 3, there'd be those of cofinality omega 2 as well. So again, they'd be disjoint and all stationary. So I could consider the sets which have got cofinality more than omega. And that would include both of these. And I could consider the collection of sets whose cofinality is more than omega 1, in which case I'd just be left with this. So that would be a thinner set. So I could get a descending sequence of 3 sets like this, each stationary, by just taking unions, of course. So let, running out of letters, P. Let P, let P0 be the collection less than omega 3, where the cofinality of alpha is greater than or equal to omega 0. And P1, cofinality of alpha is greater than or equal to omega 1. And P2, cofinality of alpha is greater than or equal to omega 2. Sorry, I realized that was off camera. So P0, points of cofinality, this is omega 0. Now each of these is stationary because the points just of cofinality omega is already stationary. The superset of a stationary set is stationary. But they're getting thinner. Like this. Now I've only, below omega 3, I can only do this because I've only got 3 possible cofinalities. Omega 0, omega 1, and omega 2. And it's smaller than omega 3. But if I now did this below aleph omega plus 1, I could look at cofinality of alpha to be greater than or equal to omega n. And I could call this Sn. Right? As I increase n, the cofinality requirement becomes stricter. So there are less elements in Sn than Sn plus 1. Each Sn is stationary. But think about what the intersection is. Right? The intersection of all of these is a point whose cofinality is greater than or equal to any of the omega n's. Right? But actually, that makes it empty because below omega sub omega plus 1, the only regular cardinals that are potential cofinalities are the omega n's. Right? So you can't be in a set whose intersection says you're going to have cofinality greater than or equal to every omega n. So I'll just leave you to check that last bit here. Okay, are there any questions there? Okay, shall I do another exercise? Exercise 226. I've got a well ordering, and I'm going to apply the Mostovsky-Shepardson collapse. And the question is, what do we get? What's the outcome? So it's inviting you to think about the collapsing isomorphism pi that's there. So recall. So in the collapsing lemma, we define some pi which will take any well-founded extensional relation on a set H to some transitive set with epsilon. So it's kind of isomorphic to any transitive extensional relation is isomorphic to an epsilon relation on a transitive set. And pi has to be defined like this. Pi of x is a collection of pi of y's where y is in H and y comes below x under R. So maybe here might be H, and here might be some y, and here's x. Right? So we do this collapsing isomorphism, and the thing ends up looking like a transitive set M here, and here will be pi of x, and now pi of y is a member of pi of x. This is an epsilon member of pi of x. Okay, everybody happy with that or not? So this is a special case, right? What we've got here is a well-founded relation because we're told it's a well-ordering. And actually, it's not a tree or a partial order. It's actually a strict total ordering, which is a well order. So what does it look like? It looks like a well ordering. Right? So here would be H and R. Right? There's a first element, a second element, a third element, and so on. So actually, of course, it looks like an ordinal. Right? So the answer is going to be that this here is isomorphic to some ordinal. And of course, it looks exactly the same. Right? it's going to be some alpha with less than over here. And so you can, to kind of justify this to yourself a little bit more, imagine what this pi is doing here. If x was the least element of R in H, here it is, right? What is pi going to do? Pi of x is supposed to be the collection of pi of y's, such that y is in H and y comes before x. Oh, there's nothing below x because it's the least element. So there are no y's like this. So this is the empty set. But what is the empty set? This is 0. So x gets sent to 0. What happens to the next element up here, z? The least element above x in the relation R. The R least element of H above x. And you can kind of now see it coming. What's pi of z going to be? It's a collection of pi of y's, again, where y is in H and y comes before z. But we agreed that z was just, its only R predecessor is x. So the only y to feed in here is x. So it's this. What we agree, pi of x, right? But pi of x is 0. And what is this? This is just 1. And that's how it's going to continue. Right? We're just going to send elements in this ordering to the ordinals. And the least ordinal that's not in the range of pi is the order type of HR. This continues. Up to some least ordinal alpha, where actually alpha is the order type. An order type means precisely the least ordinal isomorphic to the word ordering of HR. I'm assuming H is a set right here. So it's a set here with a well order. So range of pi in this case is alpha. And this is our M that we'd have got in the Mostovsky-Shepardson collapse. So in particular cases, then we get a very definite picture of what the collapsing lemma does. Right? It'll send a well ordering to the ordinal here. So in this particular case, this was alpha. We just finished with 228. Unless anyone wants to ask anything about that. I've got two transitive sets. and I've got a function between them, which is an isomorphism. Then f is just the identity. So you're asked to show this. So I'll just recall what we have for ordinals. If alpha and beta are ordinals, and f takes the ordinal alpha isomorphically to the ordinal beta, then we had in the set theory course, alpha f is the identity. The only isomorphism of an ordinal is the identity map with itself. Well, because it's the identity, beta equals alpha. So this is a strict total ordering. The epsilon here is a partial ordering in general, because we don't know anything about the sets A and B other than their transitivity. So how would you justify that this is the identity? You would do this by epsilon induction. You'd say something like, let X be in A, and assume as an inductive hypothesis f of y equals y for all y in X. Right? So everything that's epsilon below X, we've already proven f is the identity on. So then we consider f of X. If y is a member of X, then f of y is a member of f of X, because f is an isomorphism. So it preserves the order, in this case, the partial order of epsilon. All of these f of y's, we've agreed, are already y by the inductive hypothesis. So these are all y's. So f of X contains X. And now all we have to do is prove the reverse inclusion. And we'll have that X is equal to f of X. So let Z be in f of X, because f is onto there is some u over here on this side. There's u in A with f of u equals Z. So f of u is a member of f of X. But again, it's epsilon preserving. It's an isomorphism. This implies u is a member of X. As f preserves epsilon, f of u in f of z, f of X, this implies u is a member of X here. So this should give me that f of X is then contained in X. What did I do? I picked an arbitrary element of f of X here, We've said that it's f of u for something or other, right here. So I've got, in the end, f of u is a member of f of x. F preserves epsilon, so u is in x here. But u is f of u. By the inductive hypothesis, because u is epsilon below x. Down here. So I took an arbitrary element of f of x, and I showed it's a member of x. So f of x is contained in x. So with this, they're the same thing. So to recap, by the inductive hypothesis, we assume everything but epsilon below x, f is the identity, and we show x equals f of x. Therefore, for every x, this must work. For every x in A, f of x equals x. This will propagate up the epsilon partial order. That'll be the solution to that one there. Okay, fine.